our speaker.
Thank you so much, and have a great day.
Next talk is from the University of Houston, Texas, Luis Fuentes and Shubhas Thackeray.
Oh, that's me.
Okay. Welcome. I'm going to be on Ghost Mamba, a live deep learning model for tuberculosis detection from chest X-rays.
Hello everyone. It's an honor to be part of the 2026 International Conference on the AI Revolution, Research Ethics and Society. My name is Luis Fuentes. I am a graduate student at the University of Houston downtown. Today I am presenting Ghost Mamba, a novel lightweight deep learning architecture designed to detect tuberculosis chest X-rays. I would like to acknowledge my professor, Dr. Suresh Parkin, for his guidance on his research. He is currently joining us via Zoom right now. Over the next 15 to 20 minutes, I will walk you through the global TB problem, our hybrid AI approach to solving the diagnostic bottleneck. So what is tuberculosis, and how do you get it? TB is caused by mycobacterium. Tuberculosis bacteria primarily targets the lungs, but can travel to other parts of the body downstream, affects the kidney, spine, and even the brain. There are two distinct states of TB. There are latent or inactive TB. The bacteria is basically asleep in the body. But if their immune system weakens, it turns into active TB. This is when it gets bad. This is when the bacteria multiplies, destroys lung tissue, and becomes potentially fatal. Active TB is strictly an airborne disease. It's spread from someone coughs, speaks, or even sings. And germs can linger for many hours, for hours to days, depending on the area. It is in high-risk areas with poor circulation that worse. The global burden of tuberculosis. This chart is from the World Health Organization from 2024. It shows the areas that are most widely affected by tuberculosis, which include Sub-Saharan Africa, Southeast Asia, South Asia. And unfortunately, in 2024, there was 10.7 million people became infected with tuberculosis. Out of that, 1.23 million unfortunately died from it. The good news is, TB is preventable and curable, provided there is early detection and proper treatment. So here the issue is healthy lungs, tuberculosis lung. It's really hard sometimes to tell for the untrained person who aren't like radiologists which one is infected tuberculosis and which one is healthy. Before we train the AI, we have to detect tuberculosis. We have to understand what a human radiologist is looking for. On a normal chest X-ray, X-rays pass right through the lungs because they're hollow because of the air. Because the tuberculosis bacteria requires high levels of oxygen to survive, it can attack the upper lobes of the lungs first. When a radiologist looks at the scan, they are searching for specific white anomalies. The most distinct signs are cavitations, which look like dark holes with stick-up edges. The most distinct signs are the cavitation with dark holes that look like thick patches. There They also look for consolidations, which are cloudy white patches of fluid, where the fluid pools at the bottom of the lung. The bottleneck in medical imaging, the standard chest x-rays are analyzed by trained radiologists. This creates a bottleneck. Human analysis is subjective, prone to fatigue and time consuming. Furthermore, TB lesions can look remarkably similar to pneumonia or COVID-19, leading to misdiagnosis. Most important, the regions hit hardest by TB have the fewest radiologists available. AI offers a scalable solution to this, acting as a targeted second opinion to triage patients rapidly. Deep learning in medical imaging. Traditional machine learning requires feature extraction, while deep learning automatically learns the features from the data, the images. CNNs are widely used because they compute spatial patterns in medical images such as lesions and lung abnormalities. Traditional deep learning, CNNs are highly accurate, like ResNet and DensNet. They were able to detect TB and achieve accuracy in the high 90%. My direct baseline for the study was a recent hybrid model combining GhostNet and Mobile VI2, which achieved excellent results. However, it used a lot of transformers and was memory hungry. The baseline required nearly 8 million parameters. The gap we identified is deployment. A clinical and portable agent could not afford the GPUs. And our goal is to beat the baseline accuracy while drastically reducing the computation size and the parameter count. The data collection. We used 2 data sets. One was the CXR, which stands for Chest X-ray Database. It has used 7,000 images, 3,500 were healthy, 3,500 tuberculosis infected. Out of that, the training mix was 70% training, 15 validation, 15 testing. The same was for data set 2, which is the TBX11K database. Stands for tuberculosis X-ray 11,000. The data set features healthy TB and lung X-rays with other diseases. The subset I used had 800 healthy and 800 tuberculosis. I try to keep it an even split. For training, it was the same 70, 15, and 15. Data preprocessing and optimization. Because the research emphasizes efficiency, our preprocessing pipeline had to be highly optimized. We conducted our experiments on a consumer laptop, which was 8 gigabytes of RAM, and simulated real-world hardware limits. We converted the images to grayscale, resized them down from 512 to 512 pixels down to 256 by 256 to cut down on memory. The most critical step was a memory optimization technique where you casted the data set to float 16 position instead of float 32 to save a lot of memory. Essentially cut our RAM footprint in half, allowing us to process 7,000 images seamlessly. One of the algorithms used was GhostNet. Instead of computing every feature map with expensive convolution, GhostNet computes a few and generates the rest using inexpensive transformations, reducing parameters and computation, while maintaining similar performance. GhostNet solved this by generating only a small set of intrinsic feature maps using normal convolution, then creating additional feature maps from them using cheap operations such as the Wise convolution. Mamba vision and state space models. To understand why our model is so much smaller and faster than the mobility baseline, we have to look at the state space models, specifically Mamba vision. Traditional transformers are powerful because they look at the whole image at once. However, they use self-attention, which scales quite drastically. If you use double image resolution, the memory cost quadruples. This is why the baseline model required nearly 8 billion parameters. Mamba solves is using state space. Think of a transformer like someone trying to read a book by constantly looking back at every single word they already read. While in a solid state space model, on the other hand, reads the book while keeping a running summary in its head. It updates its hidden state step by step. The GhostNet extracts features. To understand architecture, we start with the local feature extraction powered by GhostNet version 2. Traditional CNNs apply heavy mass to every single filter, which consumes massive amounts of RAM. As you can see implemented over here, and the Ghost Module 2 fixes it. First, it uses standard convolution to generate a few core features, then uses cheap operations, specifically depth-wise convolution, to generate the rest. Inside the module is a DFC attention layer, decoupled fully connected. This layer calculates an attention map into quotient between 0 and 1 using a sigmoid activation. It mathematically multiplies against the features, and to simplify it, I kind of would ignore like the rip on to focus more on cloudy ones. While GhostNet looks at the local textures, the Mamba Vision block provides the big picture. In our code, the Mamba Vision block takes the 2D feature map and flattens it into a 1D, one-dimensional sequence, converted it into a sequence of patches. It passes the sequence through the Mamba layer, the state space model, using one-dimensional convolution combined with multi-head attention. This allows every patch of the lung to communicate with every patch, making it incredibly easy for the AI to spot lung symmetry. Finally, in our build to be classified per function, we alternate these blocks. We extract local details, look at the global context, extract deeper local details, and look globally again. The whole thing is poured into a 512 dense node layer with a 40% dropout to prevent overfitting. And finally, happens to two-class softmax layer that makes the finalization of tuberculosis or normal. The hybrid fusion. We alternate ghost and Mamba blocks to get the best of both worlds. The ghost blocks act as our local features, extractors, and progressively shrink the image resolution, which keeps the computational cost extremely low. Once our resolution is manageable, we inject the Mamba block to establish global spatial awareness. Comparing the left and right lines. By interleaving them, the network continuously updates its understanding of both the microscopic texture of the TB lesion and the macroscopic structure of the chest cavity, resulting in high accuracy and minimal parameters. The training and hyperparameters are used. Our training was set up so we could strictly control our reproducibility. We used TensorFlow and Keras. Using Python 3.11, the model was trained using an atom optimizer with a learning rate of 0.001 to ensure stable conversions. Binary cross entropy was used for classification. We trained with a batch size of 8, and we ran the model for up to 13 epochs. I didn't want to do more because that would just cause overfitting. We utilized early stoppage with patients of 5 and a dropout layer of 40% to prevent from memorizing the training data. Results and evaluations. Over here, the CXR confusion matrix got excellent results. It only had 3 false positives and 4 false negatives, while the TBX11K confusion matrix only had 1 false negative. It was a bit smaller. The testing set was 240 for the TBX11K, but for the CXR, it was 1,050 images. Here are the super operating curves for both the data sets. They both achieved over 99%. And both these models were ran again for 13 epochs. Here the precision epoch curve. It shows that our monitors didn't blind against TB to get a high score to maintain incredible precision, even when pushing for maximum recall. Both data sets had over 99% on the precision recall curve. Now I do acknowledge there were some limitations. For the demographics, I didn't have any pediatric x-rays from my children. They were all adult men and women. So that means the data set would not work as well on children's lungs since I don't have that information. Finally, the hardware constraints require us to downscale images, which might obscure some microscopic lesions. For future work, we plan to expand this binary model into a multi-class system that can simultaneously screen for other diseases such as pneumonia, COVID-19, or lung cancer. And test the efficiency of this model on three-dimensional scans like a CAT scan. In conclusion, Ghost Mamba proves that we do not need massive computational expensive models to achieve high results in medical imaging. By fusing Ghost and its cheap local operation with Mamba Vision's global state-space modeling, we created an AI that is highly accurate and extremely lightweight. Thank you for your time and attention. I am now open to any questions.
Questions from the audience of the work?
No question? All right. Thank you very much.
Just wanted to ask you one question that struck me from listening to the talk. You did a transformation very early on from cutting the resolution that you have from 512 to
56?
Yeah. If you hadn't done this, what would have been, you think, have you thought about if you hadn't done this kind of transformation, maybe the resolutions may have, would it have a different impact to the work?
I think it might have improved the results, but like the results were already like pretty high, 99%. It might have gotten to 99.5 or maybe even 100, but 100% I wouldn't trust that because that would like encourage overfitting.
Yeah. It just may be that you don't even need it because the rest of the processing is very effective.
That could be true, and that's something I would like to test out to see if that would be needed or not. Thank you very much.
Thanks again. We are on a break until 11. There are refreshments in the room, I guess, across the corridor. So we will resume after that. extra items.